Welcome to this explainer. Today, we're diving straight into the incredible biochemical and engineering feats of spiders, looking at how they transform a common backyard web into a literal marvel of material science. We walk past them every day, probably brushing them out of our way without a second thought. But nature's master engineers are executing an instinctual chemical mastery that human science is only just beginning to decode.
Okay, so picture this immediately relatable mystery. How does a tiny little spider cross a massive, multi-foot gap between two branches? If you've ever seen a web suspended way up in the air, spanning this impossibly wide distance, you might have kind of wondered if the spider somehow had wings. Well, the truth is actually far more elegant, and it relies totally on the environment and the wild material properties of the silk itself.
To figure that out, we're going on a quick zoom-in, zoom-out journey today. We'll look at the blueprint, the materials, the upgrades and maintenance, and finally, the future of silk tech.
All right, part one, the blueprint. Let's see how a slight breeze literally turns into a perfect geometric trap. The whole process kicks off with spinnerets. These are tiny organs on the spider's abdomen, and honestly, this blew my mind. A spider doesn't just squeeze out silk like toothpaste from a tube. It physically pulls the liquid silk from its internal glands. As it pulls, it instantly hardens into a super lightweight, incredibly strong thread, right at room temperature. Different spiders can have multiple spinnerets working independently or completely in sync.
So back to crossing that gap. The secret engineer here? It's just the breeze. The spider lifts its spinnerets into the air and releases a lightweight silk balloon. Since the silk is lighter than cotton, the wind, or even just a tiny thermal current rising from the ground, carries it until it snags a distant branch. It sticks via tangling or static electricity, kind of like a balloon sticking to a TV screen. Once it's anchored, the spider just tightrope walks across to reinforce that crucial first bridge line. Once that bridge is up, pure instinct takes over. The spider drops down to build a strong outer frame out of non-sticky silk and adds straight spokes just like a bicycle wheel. Then it weaves a loose, temporary scaffold spiral from the center outward. Finally, it works in reverse, from the outside back into the center, laying down the actual sticky trap spiral filled with glue droplets and eating that temporary scaffold along the way. Amazingly, an orb weaver spider can pull off this entire architectural masterpiece in just 30 to 60 minutes. Moving right into part two, the materials. Let's zoom way in on the microscopic chemistry to understand what makes this silk stronger than steel by weight. Spider silk is basically a natural polymeric protein in the exact same family as the collagen in our ligaments. The specific proteins are called spidroins, and they're mostly packed with two of the smallest amino acids, alanine and glycine. Because they're so incredibly small, they can pack together extremely tightly inside the spider during that spinning process. Here's where it gets its superpower, a dual structure. You've got these crystalline regions formed by the alanine. They're stiff, highly ordered, and provide immense tensile strength. But then, you have the amorphous regions formed by the glycine. These are loose, spiral coils that are super elastic, letting the web stretch up to 40% without snapping. It is essentially like having microscopic bricks tied together by elastic springs. Think about an insect hitting the web at high speed. If the web was stiff as glass, it would shatter. If it was purely stretchy, the insect would just bounce right through. Instead, those amorphous coils instantly absorb the impact, while the rigid crystalline bricks bear the load so the thread doesn't break. They work together perfectly. 520. That is the massive number of megajoules per cubic meter of energy that Darwin's bark Spidey's dragline silk can withstand before failing. To put that in perspective, that level of toughness absolutely blows synthetic Kevlar out of the water. It's this exact biological formula that allows that specific spider to cast giant webs completely spanning entire riverbanks. Zooming back out to the macro level for part three, upgrades and maintenance. How do spiders survive in and maintain these high-performance structures?
You definitely might be wondering, with all those glue droplets designed to instantly immobilize thrashing prey, how does the spider freely navigate it? Why doesn't the architect just get trapped in its own snare? Well, they use brilliant anti-adhesion tricks. For starters, they mostly tiptoe on the dry, non-sticky spokes. But when they do touch the glue, dense arrays of branched bristles on their legs, called setae, severely minimize the surface area making contact. Add to that a very careful way of stepping and a special chemical non-stick coating they apply to themselves during grooming, and they're completely safe. Some spiders even upgrade their webs with a stable momentum. These are heavy, conspicuous web decorations made of thick silk zigzags, egg sacs, or even plant detritus. It helps them camouflage, deter predators, or attract prey. And fun fact, seeing these exact decorations is what inspired E.B. White to come up with the writing spider for his classic book, Charlotte's Web.
Of course, nothing lasts forever, especially a web battered by the elements. Enter nature's ultimate recycling program. Because synthesizing that protein is highly energetically expensive, spiders don't abandon damaged webs, they eat them. By consuming the old silk, they reclaim those vital proteins and nutrients, saving huge amounts of metabolic energy and ensuring they have a fresh, highly effective trap ready for tomorrow. And finally, part 4, the future of silk tech. Let's explore how humanity is pioneering cutting-edge biomimicry from all this. Biotech firms like Craig Biocraft, AM Silk, and Spiber are actively genetically engineering proteins right now to mimic spider silk. Because it's lightweight, stronger than steel, water-resistant, and entirely biocompatible, we're talking about next-generation applications like medical stitches, artificial ligaments, advanced body armor, and even lightweight spacecraft components. Seriously, nature's master engineers have been at this, building perfect traps, for over 300 million years. They produce millions of tons of this biodegradable supermaterial globally every single year without toxic chemicals or high heat processing. They're executing a chemical mastery that science is only just beginning to replicate. So, what will they build next using these 300 million-year-old engineering secrets? The next time you look at a web in your backyard, catching the morning dew, ask yourself, how will human innovation completely transform once we finally master the secrets woven into these silken threads?